like the University. He is the leader of the research team of computational physics at the Starwatch Leiden or Castle. And one of his most important activities was the development of the Muse software that we are learning here at the Astro with the teacher Simon. And today we have his seminar about simulation of the Milky Way galaxies by a star-by-star basis. I leave you with the teacher.
Thank you. Well, thank you for the nice invitation here, and being here in Colombia is really a pleasure. The weather is very nice, and normally I would have a warm jacket to protect me against the cold in the Netherlands at least, and it is raining very heavily right now in the Netherlands, but on the other side of the planet here it's beautiful. It's very good to be here. I'm also happy to see many of non-students, at least non-students in the class for the computational astrophysics, and also the students, of course. So there will be some overlap maybe, but I don't think too much. So I try to make it as non-overlapping as possible. And this is a completely different research project we have been doing over the last few years. And the idea is to, it started that several years ago, when I wrote to a friend saying that GPUs were very much coming up. GPUs are the graphical accelerators you have in your computers. And the fun thing with GPUs is graphical processing units is that they're very cheap. They cost almost nothing, like 200 euros you have a graphical processing unit, and every PC has one these days. And the other fun is that you can buy them anywhere and everywhere. I can go out of my door of my house to the computer store next door, and I can buy a high-power computer. I can buy a teraflop computer for 300 or 400 or 200 euros. And at that time, it wasn't clear that this development would develop like such. And there was also the FPGAs, the field programmable gate arrays, which were very upcoming. And then we made a decision on graphical processing units to use those for accelerating our calculations, which was extremely successful. And now we can do a simulation of the galaxy on a star-by-star basis, so 100 billion particles. And then you have to imagine, if you have any idea of the scale, the previous largest simulation of the galaxy uses 100 million particles. So we do 100 billion particles. It's 1,000 times more, actually 2,000 times more than anything done before. And that development is only in the last few years. So in a few years' time, you make a step in modeling the galaxy on 100 million particles or 100 billion particles. And it's due to the software advances and to the hardware advances. And I will tell you a little bit about that. So this is one of the renditions we made. And at the moment we did the calculation, the Sterrenwacht was, so the astronomy department in Leiden was sort of renewing the wall paintings and things like that. And somebody saw a picture and says, oh, we should have that as a wall decoration. So we have a 20-meter long wall, something like that, what you have on the back side or here on this side. And we have this image blown up to the size of this entire wall in the astronomy department. So if you come visit, you can see this galaxy being magnified very large.
Good resolution.
Well, this is the resolution of 100 billion particles. So you can go with a microscope, you can go to the wall and say this star and this star, is an interesting pair, It's an interesting thing. We did actually something very similar with a cosmological calculation, which is one floor down at the same department, also in a very long wall. And then it's also very high resolution. Also fun. If you ever think of going into computational astrophysics as a profession, be aware of one thing. That is, as a computer astrophysicist, it's very hard to sell your research. Because if I send my papers to a computer science journal, they will say, come on, this is astronomy, we're a computer science journal. And if I send my results to an astronomy journal, sometimes they say, well, this is not astronomy, this is computer science. Why don't you send it to a computer science journal? So in order to solve this problem, we started our own journal, which is called Computational Astrophysics. And I happen to be the editor-in-chief, but before I was the editor-in-chief, there was another editor-in-chief, and he says the journal should be called Computational Astrophysics and Cosmology. But I would think that you can cross out the cosmology here and say planetary science or computational astrophysics and stellar evolution or computational astrophysics and the first biological molecules, or computational astrophysics and chemistry, right? I don't see this second line there. That it's a bit weird, but computational astrophysics. So I encourage you, if you have a computational astrophysics result, to publish it there. It's open access, and I can give you a wild card, so you no page charges, right? So this is the editorial team. So this is now less than 1 year old. It's a really very young journal. I'm very happy with it. Now, if you look at computers, if you're a computational astrophysics, you use telescopes. I don't use telescopes, right? My friends use telescopes. And they use computers. I use the computers. And then there is a sort of a fight between theorists and observers, but there is an even worse fight between observers and computer scientists. Because the computer science has been growing so dramatically over the last years, but the telescopes they go very slowly, right? I mean, the bigger telescope, when is it? You know, the ELT, you know, when will it be built? What was it now, 38 meters or 40 meters? I forgot, right? And it takes years and years before they build a new telescope. And 40 meters, what is the next biggest telescope? It's, I don't even know, 18 meters or so, or 16 meters? So you go a factor of 2 in 20 years. But if you extrapolate that, and if you look at Moore's law, you know Moore's law from computers, that the double computer speed, roughly speaking, every 2 years, right? Computers get twice as fast every 2 years. Telescopes get twice as big every 80 years, right? So the ELT is not so bad compared to the VLT in that sense, because there's only 40 years between that. So they make a big jump, actually, the observers. So Moore's law for telescopes started in 1608 with Lippershey in the Netherlands, in Middelburg, looking through his little telescope at the little cock on the moon. So we have little cocks on the moons, on the moon, on the cook on the church tower. And then to this thing takes 400 years. So you have an 80-year doubling of performance in telescopes. And if you doubling, I mean doubling of the collective area, right? Now, at that time, there was astronomy and there was physics, right? Physics was a different job. So astronomy and physics got merged into astrophysics. And in astrophysics, you could then do theory and you could do observations. And now we have more pillars of science, so to say, which you can represent with the, you know, the nice Greek story in Europe, so to say. But you still have the nice pillars, independent of their economy, of course. But the pillars will stay there. But the pillars of science are now not only theory and observations, but you should add to that computing. And you should add to that data. Isn't it a bit weird? I mean, we had 2 pillars of science, theory and experiment, or observations and theory, if you like, for 2,000 years. And now, in the last decade, we added 2 to those. We doubled the number of pillars of science, so to say. So I wonder which of the 2 will go away, or how many more we are going to have, right? So data is a completely different science than computing. Now, Moore's law in computers is sort of expressed here in the evolution of, or the speed of people, or the speed of thinking, if that's the other way I like to do it. So if you start at the 1900s, you can have 1 billion floating point operations per second, so the speed of a computer, so to say. Well, there were no computers at that time, but you can still compare it to sort of manual calculations. Do it by hand, right? Everything was done by hand. And how many floating point operations do you have by hand? You know, how fast can you do your calculations? How fast do you do?
One sum per second.
1 sum per second, right? Yeah, I think so too. I mean, we're equally fast, you know, we're similar computers. But if you now see where we are today, in 2015 or 17 almost, we have 1 billion instructions per second. We are approaching human beings. We are approaching the speed that a computer actually is overtaking us. Our brain, right? My brain, before I die, well, I hope, right? Before I die, computers will be faster than me. That doesn't mean they can drink coffee, because if I give coffee to my computer, I try that actually in practice, it dies, right? It just dies. I can drink a lot of coffee before I die. It can't make coffee, that's good, because it would die if it did. But even though we can make computers which are theoretically as fast as people, they still cannot do everything. But they can do certain things do very well. For example, let me give you an example. A year ago, or 3 weeks ago we had the Computer Chess World Championship in Leiden. And you lose, you all lose from any computer, even this laptop, playing chess. Even if you are the world champion, which I don't recognize here being sitting here, but he loses from my laptop if he plays chess, right? So any computer game you play on a computer is tuned to play worse than you, or maybe about equal. Think about it, right? It's a lost game. Now, if you go back to astrophysics and to sort of the complications you have in simulating the entire galaxy in a supercomputer, you have to think about the size of Earth. If that's the thing you want to resolve in your computer, the size of Earth is about 10,000 kilometers, right? Now, the Moon is about 400,000 kilometers away. So you have to resolve the size of Earth compared to the distance to the Moon. And you have to resolve that with the scale of the whole galaxy. So would you like to resolve the planet and the Moon, the Earth and the Moon, on a galactic scale, you need about 20 digits in your computer. Now my computer has 16 digits. So how do I solve those 20 digits even though I only have 16? So I can't resolve the size of Earth on a computer if I'm interested in the entire galaxy. In the time scale, something similar. The orbit or an event which may be interest to me may take hours or minutes. Millisecond pulsars, for example. I'm interested in a millisecond pulsar. The time scale for a millisecond pulsar is about a millisecond, right? Maybe 100 milliseconds. But the lifetime of the universe is 10 billion years. So that's also 20 orders of magnitude in scale, in time. And even then, I only have 16 decimal places. So how do I solve that? How do I solve all these complexities? And then you have all the physics. You have hydrodynamics, stellar evolution, gravity. All the physics comes together in simulating a universe. So the strengths of being a computer scientist and the problem of any observer is that we can ignore everything but. And ignorance is the most important thing in computational astrophysics. You have to ignore as much as you can. So you ignore the rest of the universe. The galaxy is just the galaxy. I don't care about anything else. I ignore the interstellar gas. You know, it's only 15% of the mass. Who cares about this 15%? I ignore magnetic fields because the physics is so complicated and it takes a lot of computer cycles to solve it. I ignore the evolution of the stars. I ignore the presence of planets and planetesimals. I ignore human population, even though I know that one of the planets in my simulation should have a human population. Otherwise, he couldn't do the simulation at all. So we ignore everything except gravity. Well, gravity is fun because gravity has a negative heat capacity. Well, do you know about, well, the students now know, my students now know what the negative heat capacity is. Do you all know what about the negative heat capacity of gravity? The negative heat capacity. So we live in a universe with a positive heat capacity. Well, I mean the universe, we live on a planet where the heat capacity is positive. That means if I put in energy in my coffee, it heats up, right? If I'm driving a car here in Medellin and I slam the brakes, it will go to a stop. If I live in a negative heat capacity universe, it's the opposite. I'm riding in Medellin on my motorcycle and I slam the brakes and I go faster, which is not a good thing, right? Because they're driving already very fast. So the negative heat capacity, everything is turned around. Your intuition is on its head. And that makes it very complicated. The force calculation is n squared. That means every star pulls at every other star.
But why gravity has this negative?
Oh, you can just do it. You can do the dE. The negative heat capacity is just a derivation of the energy by what you put in. So what's the response? And in gas dynamics, for example, it's positive. But in gravity, it's negative. So you can just do the calculation. And you know it, for example, if you have a satellite in orbit around Earth, right? You have a satellite, and it has a little bit friction off the top of the atmosphere. What would happen? Think about it.
Fall down.
It falls down. So it comes into a lower orbit. What happens to the speed of your satellite?
Increases. Yeah.
It increases.
Okay.
So the satellite has friction. The friction causes to go faster. You don't think about it, right? If you get mechanics. But it is quite funny, right? So due to friction, the satellites go faster. That's a negative heat capacity universe. There is no shielding of gravity. If you do molecular dynamics, I have a bunch of electrons here, or whatever I have, and I have a bunch there, but they're shielded from each other. So you don't feel a force over large distances, because you have positive and negative charges. Gravity has only one charge, right? It's always attractive. You don't have a repulsive gravity. Oh, science fiction movies, of course, you have, but you know, we don't know about that. So there's no shielding. It makes it very complicated. So that means that the star on one side of the galaxy feels the gravity of the star on the other side of the galaxy. And you can't ignore the other parts. The small distances are very important. So small differences and small perturbations means large forces, and therefore they drive the evolution of the system. So you have to take the small scales into account together with the large scales. And worst of all, the equations of motion are intrinsically chaotic. What the hell does that mean, right? Well, I'm not sure. Let me try to give you the view of chaotism. Chaotism is a sort of a fancy word. If you use it in proposals, if you write proposals to get a PhD position or a postdoc position, you should write big data, chaos, non-linear response to initial conditions, that sort of things, right? Because then you are more likely that the people who read it don't understand what you're saying, and therefore you get a job. But chaos means basically that you're very sensitive to initial conditions. If I go from here to my hotel, I'm not very sensitive to my initial conditions, because I take the subway and the subway stops at another stop, and that's where I come out. And the subway always takes the same track. So the subway in Medellin is not chaotic. If I take a walk from one side of Medellin to the other side, I never know where I end up, because I may take a wrong street and I go to the left and suddenly I don't know which direction I'm walking. So the walking from one side of Medellin to the other side is very chaotic. And if I start one street to the left or one street to the right, I may end up in a completely different location of the city. So walking through the city, I experience as being very chaotic. So it means intrinsic sensitivity to initial conditions. And then you can wonder, what is sensitive mean? And what does intrinsic mean? Now, sensitive means that if on the position of my laptop, which is 16 decimal places, I make a small error, deliberate or undeliberate, I get a different answer. I'll give you an example. You don't have to stay in the uncertain part. Now, simulating the galaxy is extremely expensive, because you have to solve the n squared problem. Now, with 100 billion particles, the number of stars is 100 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 10 to the 11 stars. The number of interactions is n squared. So that is 22 zeros. Have you counted them? Yeah, good. The number of steps, the number of integration moments I have to take, the number of operations I have to take is about 100,000. So I have 100,000 times 10 to the 22 is this number of flops for one calculation of the force of each particle. So each star, then I have a force on each star. I didn't even do the evolution of the galaxy. I just do one force calculation. Then I have to move all the particles and do the whole business again. So I have to do this as often as the galaxy is old, basically. Now, we don't have a name for this number of floating point operations in a computer. This is a petaflop. You've heard of petaflops? Do you have a petaflop computer in this country? What's the fastest computer you have?
No, it's teraflops.
Teraflops. So this is the fastest computer in your country. This is a petaflop. This is a petaflop. This is a zetaflop. This is called a yottaflop, and here there is no name for it. So we don't even know how to call the performance your computer needs in order to do this. Now, it's clear that we can't do this, right? So you have to be smart. Now, look at the image. I love this image, right? This is. Do you know this image? This is an artist's impression of the Milky Way. This is not even a real galaxy, right? This is a fake galaxy. It looks like a real galaxy, but it's a fake galaxy. And they made it together with astronomers, artists and astronomers, to make a picture which looks really like the galaxies. They can put it on press releases. Press releases are fantastic things, because there's always complete nonsense. And in this case, a complete nonsense. Do you know what we know about the galaxy? It's this. This is how we know that the galaxy looks like. This is a map of the galaxy today. right? And everything we know, all the stars you see on the sky are in this little point. All the stars in the Hipparcos database are in this little point, right? We don't know anything of stars here, except for a few neutron stars, right? You can see them due to radio, or maybe due to a few Wolf-Rayet stars. But this is our map of the galaxy. But Gaia, of course, is going to change that. Gaia is going to view 1 billion stars of the galaxy, positions, velocities, colors, something about composition. So we get a full map of a big part of the galaxy. And we would like to match that. We would like to match that with a simulation. And then say, hey, we have a map of the galaxy from Gaia, and we do a simulation. And then we compare the two, and we say that's wrong. Is Gaia wrong, or are we wrong? Probably we are wrong, right? So then we do a new simulation, until we have a match with these billion stars. And then we may have learned something about how the galaxy looks like. And we can maybe fill in the parts that Gaia cannot observe. So that's the reason to do it. Now, if you look at this unnamed number of floating point operations, this super duper fast computer you need to do that, you can look at the history. This is sort of the history of computing in gravity. And you look at 1960, the first M-body calculations were done by Sverre Aarseth. And that was with 16 particles. And it was in 1964. And then he did more calculations. Oh, here's his 16-body calculation, I think. And then you see how it advances. And this is the number of calculations he has to do divided by the number of transistors, divided by the speed of the computer he had. And you see that everybody is equally fast, equally fast, equally fast. There are a few, of course, I put my little calculation there to advertise my own work. But it was just little calculations, not really a fair point actually, right? So, but it's okay. So it's sort of horizontal. And then we discovered the GPUs, the graphical processing unit. And this is the same image, but this is our galaxy simulation. So this is this factor 1000 I talked about. I mean, it is so much faster than anything else. And we do it with a little code we wrote, and we call it Bonsai. And today on AstroPH, actually, there's a paper about Bonsai written by a completely different team, by Rainer Spurzem and his colleagues. And they compare Bonsai with M-body 6++. And M-body 6++ is like a completely different ballpark to compare with. So you should read the paper. It's fun. It's fun. It's a completely unfair comparison, but therefore it's a lot of fun to do. So Bonsai is small but strong in the force, right? Just like maybe you should have called it Yoda instead of Bonsai. And Bonsai, of course, is available in the Muse. Now, the way how you develop such a code is as follows. You write a code, you buy a computer, and you put in a GPU, you put in a graphics card, and you write a code for one PC with one graphics card. And then you put in 4 graphics cards, and you start to parallelize it. And then you have to redesign your algorithm. Everything has to be rewritten. And then you buy a second PC, and a 4th and a 5th. And then you have to rewrite the entire code again, because the architecture changes and all the bottlenecks in your code will be different. And then you go to the first real supercomputer. In this case, it's Cuba, where you have 400 GPUs. And you have to rewrite everything again. And then you go to a bigger computer, which has 4,000 GPUs in Switzerland. And you have to rewrite your code again. And why do you have to rewrite your code every time again? You have to imagine, this is a tricycle. This is on which I learned how to ride a bicycle. This is your first car, right? If you go from a tricycle to your first car, you have to relearn how to ride. Because you don't have to balance yourself, you know, you can sit, right? And you don't have to steering wheel like this, but you do it like this. You have all kinds of things to do with your hands. So it's completely different. If you go from here, from your first car, to here, it's like going to a Ferrari. Well, riding a Ferrari is different than riding my first car. I'm not sure, because I never rode a Ferrari. But I think it is quite different. Going from a Ferrari to a jumbo jet is the next step. Well, if you can ride a Ferrari, I'm not sure you know how to ride a jumbo jet. But I never tried that either. But if I look in the cockpit, I see a lot of lights. And going from a jumbo jet to the Starship Enterprise, right? So every time you have to rewrite the code completely from scratch. It took us 7 years to do that. 1, 2, 3, 4, 5. It's 5 steps in 7 years. It's a lot of time. But we managed. So in the end, we run on Titan. It was the biggest computer on the planet at that time. You know how you get time on Titan? It's an interesting story. So this is one of the biggest computers on the planet. So we wrote a proposal, and we say we want to use this computer because we are running at that time on this sort of machines. This sort of machine we were running. We hadn't done this step yet, but we knew we would be in trouble. And I wrote a letter to the supercomputer center. I said we want to use the supercomputer full force on simulating the galaxy. And the proposal committee says, well, you know, this team is from the Netherlands. Come on, you know, they don't know how to program computers. It's a third world country in computing. And so my proposal was turned down. But the director of the computer center, he has his own time, he read my proposal and he says, well, you know, let's assume that they can. You know, it sounds quite exciting to simulate the galaxy on a star-by-star basis. So he phones me and he says, can you do it? I said, yeah, sure, you know, yeah, of course we can do it, right? I think we can do it. Okay, he says you get 1 day, 24 hours on the machine. So we got 24 hours, and this is like 24 hours in enterprise, right? I mean, think about it, right? I don't know where I would go, but engineering, bridge, you know. 24 hours on the machine, so the whole team was ready. We had Michiko Fuji in Japan, Jeroen Beedorf was sitting in Leiden, and I was in the United States visiting, and we had a full contact. We worked 24 hours through the clock, and of course everything failed. But after 24 hours, Jack Wells, the director of Titan, he phoned me. He says, you know, I see it's going very well. I said, you know, going very well? It's not going very well at all. Well, you know, you were running on 25% of the machine. You want another 24 hours? I said, yeah, it's okay. Let's give me another 24 hours. So we got another 24 hours directly following up. And we were awake for 48 hours. And he phones me again. He said, well, you know, I think it's going very, very extremely well. You get another 24 hours. I said, no. If you want to kill us, you do this. But give us a month or so to analyze the data, and then, you know, we would like to have our other 24 hours. And we did. And we did it another time, and we did it another time, and then we got 100% performance, well, 95 point something percent performance on the machine. And we got nominated for the Gordon Bell Prize for it. The Gordon Bell Prize is the Nobel Prize for computer scientists, so to say. There's no money involved, you know, don't worry. But it's, if you're really pressing a lot of performance out of a computer, you get this sort of no money prize. It's a sort of an honorary thing. And you even have to pay your own ticket, your own hotel, and you know, your own food in order to get there. And here it's better because, you know, it's all paid. You know? You can better go here than go for the Nobel Prize, for the Gordon Bell Prize nomination. This is how we did it. So this is an image of the galaxy from top, the simulated galaxy. And instead of using direct and squared, we use a tree code. So we say things which are far away, I take together in boxes. Here you see it. This is sort of a two-dimensional representation. Well, the galaxy is two-dimensional also, sort of, right? So you have stars, the blue points, and instead of calculating the forces between all the points, you calculate the forces between all the points in this box, or all the points in this box, with that point, right? I don't care if the particle's here or there for this one, but I just take them together and calculate one force. If you look at Andromeda, I can say there is an Andromeda left and Andromeda right. It saves me 10 to the 11 operations, right? It's very efficient. So that's how we did it. But then we didn't do the parallel yet. You still have to parallelize the whole thing. So we put in a lot of techniques in order to, how do you program not one computer, but how do you program 3 million computers, which are all sitting together in a room like this. It's a bit bigger. It's a bit as big as this building almost. And they have 3 million computers in that building. And how do you get them all working on the same problem together? Well, that is a challenge. And you do that by domain decomposition. You say, I put the galaxy, I make the galaxy into little chunks. And here I have a small number of chunks, not you know, 30 million. Because, you know, I don't know how many pixels I have, but, you know, it's of the same order. But you see, I put the galaxy in different parts. And each code, each computer gets to solve a little part of the galaxy. And then you put it all together again. And the trick is to use the graphics cards as much as possible, because those are very fast and very efficient. So you want as least communication as you want. And then you get this graph in the end, which shows the performance. Have you ever seen a graph like this? Yeah? Well, I haven't, right? Well, I have because I made it, but it's you know, all the graphs you see, this is a performance graph. And here you see the number of graphics cards. We should have CPUs, but then it goes to 3 million. And I doubted that your screen would be large enough. So I do graphics cards, nodes, 18,600. We didn't do the full 20,000 because there are always a few nodes broken, a few computers always damaged. You know, if you run on a computer which has 3 million chips, every hour a chip dies, right? Imagine you're running, and every hour you're running, something breaks in your computer, right? It's like riding a car, and every hour you're riding, you know that something will break in your car. That's how these big supercomputers work. But basically, they don't work, right? They're down most of the time because they're so big, they're so complex that they all break at some point. Something breaks. And it's not bad, right? I mean, it's just the way things work, right? If you have 100,000 hard drives, you know, every moment a little one. At this whole university, how many light bulbs do you have? I'm sure that every hour a light bulb at this university will break somewhere, right? But you can't predict which one where. So it's just physics. It's okay. So this is the speed of your calculation, and this is the number of codes of computers you have. Now, if the number of computers increases, you want your speed of your code to increase too. And ideally, if you double the number of computer components, you would like your code to double in speed. And that's why you get a straight line. Now, graphs you have seen of this sort stop about here. And then they turn over, they go down. And they go down because if you increase the number of processors, your code actually will start becoming slower. So some of the students have seen that already using Amuse in the lecture room by solving a 3-body problem on 4 cores. Well, of course, you don't get any speed, right? Because you only have 3 particles. So the computer has nothing to do. The only thing the computer is doing is communicating with itself. You want particles? Out of processor, yes, I want particles. Okay, here you have the X and the Y positions. Well, thank you. What should I do with it? Well, so that's how the computer works internally, right? So it's very inefficient. And actually, it's even worse than this, but you know. So the performance goes down, but this goes on and on. When I show this picture at a computer science conference, you know, people start really, you know, shedding tears and so. You know, it's fantastic. Well, of course, you want to see a movie, and I don't do a movie of a single galaxy, but I do a movie of the Andromeda Milky Way galaxy. And the reason is, it's nicer, right? I mean, the Milky Way is a very boring galaxy. It's just rotating. There is some spiral structure. But now you have 2 galaxies, right? You know, come to one in. It's much more interesting what happens. So of course you know what happens. They will merge eventually. And this is a run we did online. So we had a laptop. Well, we had a laptop which was connected to the supercomputer, and we run the simulation on the supercomputer and get the images back on the laptop. And that's why it's interactive. So it's why you see the cursor here. So we move around. So we stop it for a moment, and then we turn it around, and we look from another side. So this is a test run, actually, with 50 billion particles. And you see how we sort of play around with it. And this is done an image you make it a little bit different, and we filmed it while doing this. I don't know what it's doing now. It's still running.
How many particles?
It's on the screen. What is it? This is 50 billion. 50 billion.
50 billion.
Yeah. But the part of the presentation was made with help of NVIDIA. And they wanted a shiny thing, so most of the particles you don't see. So all the dark matter particles you don't see here. And some of the stars they make extra bright, so you sort of see, I don't know, star clusters, maybe? Right? That's why you see only so few particles. Right? So these are extra bright particles to make it sort of a starry, shiny thing. So this was run on Titan. Now, if you simulate the entire galaxy, the entire Milky Way, with a tree code, you solve the equations of motion of all the particles, of all the stars, with a sloppy force calculator and a sloppy integrator. Actually, you do a very bad job astrophysically. And you have to, because otherwise you couldn't do these 100 billion particles of the whole galaxy. So you have to do a sloppy job because there is so much work to do. So the only way you can do much work is by being sloppy. So if you look at people who write 20 papers a year, you should wonder if the papers are all as good as they think they are, right? Maybe they are also sort of speed up and compensating speed for quality and quantity. You can better write a few papers a year, good papers, right, as a scientist. But there is another thing in astrophysics, and that is what we said before, is the chaotic, intrinsic chaotic quality of gravity. So if you simulate something sloppy, how do you know that you get the right answer? Well, you don't. You probably actually get the wrong answer, because gravity is like the weather. If a butterfly flaps its wings, it may start thundering somewhere else later, right? And the errors in embodied simulations are building up and driving in part this chaotic behavior, and therefore driving the physics, which actually is not physics because it's introduced by your errors you make. Let me give you an example of this. I was in Tokyo. In Tokyo you have sumo. You know sumo? Sumo is this sports where you have these big wrestlers and they try to smash each other out of the ring. And there's an interaction between the binary sumo, so to say, and the rest of the audience. And what happens with the two sumo wrestlers depends on what happens to the audience, but not always. So we saw this one. So you have the two sumo wrestlers. Now I should remember his name, but I don't. And the other. I was at this match. This was taken from a later. Yeah. Good. Okay. Well, I know his name, but it's. Yeah, he's Hawaiian. They're both Hawaiian, actually. So there they go. They start. So the audience you see is sort of the galaxy. This is a binary in the galaxy. And you have to look at the left, where he flattens a cameraman. So the rest of the galaxy never knew what happened in the core until something was kicked out and interacted with the outside. Well, can you resolve this in your calculation? If this is chaotic, it's very hard to do that, right? And how do you know that it's the right thing? If this was the result of a calculation, you may have mistrusted this. You said, well, how likely is it that one of my particles is ejected, one of these massive particles is ejected and, you know, hits the sun? You would say, you'd throw the calculation away and say it's not true. So we wrote another code, which we call Brutus. And Brutus is nice because it goes beyond the precision of your computer. Your computer has 16 decimal places, as I said before. This code, we can go to 300 decimal places, or 10,000 decimal places, or 100 million if you like, right? It doesn't make your computer faster, obviously, but it makes the code much, much slower, but you get the right answer. So you can get the absolute right answer. If I use this code in my walk back from here to my hotel at the other side of Medellin, I will go the exactly shortest way I can have, right? And it will not be chaotic. So you can fight chaotism, numerical chaotism, using smart algorithms and being a bit precise about it. Let me give you an example of a chaotic three-body system. So we had a chaotic two-body system, which is very rare in physics. But a chaotic three-body system is this one. Well, I hope it's coming. Yes. So there are 3 stars, and I should start it again, right? So there are 3 stars, and I do 2 calculations on top of each other. One with a sloppy integrator or normal integrator you would normally use if you use embodied integrations, and one using Brutus to the moment that we are absolutely sure that the only thing we see is physics. So we solve for the physics, right? And we needed 1,000 decimal places, 1,000 places behind the comma to be able to solve this accurately. And the sloppy calculation takes about a second. The accurate calculation takes about 10 minutes. Well, a little bit more. It was not 10 days, but it's more than 10 minutes. It's quite longer. And in red is one calculation, in black is the other calculation. And they start at exactly the same positions and velocities and masses. And it's what we call the Pythagorean problem. So the stars are in a triangle, equilateral triangle, Pythagorean triangle, I mean, and the masses are 5, 3, 1, etc. And the velocities are 0. So they fall together and then they start evolving. So have a look. And I want to know from you, what is the correct calculation? Which of the 2? So there's the red one and there is the black one. Can you see the difference in colors? Yeah, you can, right? There we go. And can you, so one calculation is completely different from the other, right? So they have diverged on what you could say dynamical timescale, the crossing timescale. What is resolved? What? One escapes. One resolves. And the others still go, and now it resolves. So which is right? Who is for black? Who says black is right? Who says red is right? Who says both are wrong? Oh, black is right. Well, we did 1,000 of those in different. What?
Red is right.
Black is right.
Oh, red.
Black is right. Is red right? Oh, red's right. Okay, red's right. It says it. Ah, damn! I thought it was black.
The answer is there.
Is it really true? Is it true?
The screen.
Okay, well, it's the screen. It's to confuse you. So you can't even see what's right. And actually, it doesn't matter which one is right. If you're not interested in exactly where the star is at that moment of time, what you care about is if you do a large number of those triple encounters, is statistically getting the same result with a sloppy integrator as you get with an accurate integrator. So if I do 1,000 of one with a sloppy integrator, it's a bad computer code, and I do the same initial realization of those 1,000 with the absolute accurate code, statistically you hope that you see no difference between the right code and the wrong code. And that is good news for everybody who has been doing computational astrophysics so far, because it turns out to be the case. I had hoped that it was not the case, because then we would have submitted this paper to Nature. But it was the case, so we published it in monthly notices. And here you see the result of 1,000 calculations with Brutus and 1,000 calculations with Hermite. Hermite's a good code to use. And this is the time it takes for resolving the triple. How long does it take before they fly apart? And you see that it is sort of, the line here is that it takes in Brutus as long as it takes in Hermite. So those are the calculations which are accurate in the sloppy integrator in Hermite as well as in Brutus. And the rest is statistically distributed homogeneously along the symmetry axis, meaning that there are as many simulations which take longer as simulations that take shorter in the accurate compared to the inaccurate calculation. And it means statistically, if you have a large number of simulations, we can't make the difference between was this population integrated with an accurate integrator or with an inaccurate integrator. So don't trust any individual orbit you calculate with any embody code, except if you calculate it with Brutus. But statistically, you're fine. So if the galaxy is composed of many triples. So we think now that a sloppy integration of the galaxy is fine, because it's sort of a statistical averaging over the calculation. Let me show you one other thing. That is how you do it with a 16 body. This took about a year to run. So this is 16 bodies, red and white, and one is accurate and the other is not accurate, but I don't know which one is which. And this is the phase space difference between the two simulations. You see how the error sort of grows in logarithmic units from initial to 1 in about 10 crossing times, 10 dynamical time scales. So it takes 10 time scales before this deviates completely, and you can't recognize one from the other anymore. Okay, final slide. We run on Titan, on 20,000 nodes almost, 90% efficient, getting 25 petaflops. The fun thing is, the Dutch national supercomputer has about this speed. Right? That is our national supercomputer. So this, you can see how we are in this third decimal place of what we did. Simulate the galaxy of 1 giga-year in 1 day. So we need 10 days of Titan time. Now the question is, do we get it? It's all on the GPU, load balance, communication, everything is parallelized. And we believe the results, because statistically we're doing the right thing. That's all.
I have a question concerning the code, specifically the good balance you present in domain decomposition and those things, because when you do piano per domain decomposition, actually one needs a lot of communication between the different domains to sharing particles and those things.
Yeah.
And doing it with the graphic cards somehow will imply to move a particle from the graphic card to the CPU and then back to
another graphic card somewhere.
Yeah.
How do you manage to pick the efficiency of this transit of information across the processors and those things to make it work the way it does?
Yeah, you're completely right. So the question is, if I translate it in more human terms, is that the communication between the PC and the graphics card is very slow. So it's very hard to get data from one graphics card to the PC, over the network to another PC, to its own graphics card, right? So there are 3 steps of communication in between. And how do you hide that communication and make still sure that everything is working properly? That is very complicated, I can tell you. And that's why it takes so many steps, and that I compare Titan with running on Enterprise. And let me see if I have a slide on it. So let me explain in an easy way. And I can tell you the details. In Titan, a node is composed of 1 graphics card and 16 chips, 16 CPUs. And we use all these 16 CPUs to splice and slice the data, so we're absolutely sure that the data is sent to the right computer. And for each GPU has about 100 million stars or so, right? And well, a little less, 10 million stars. A few 10 million stars. And all the 16 cores are working exactly on this communication issue.
Okay, so
and that's why it's so hard to write such a code.
You're not using only CUDA, but MPI CUDA?
No, this is MPI with CUDA, and so the GPU code is completely written in CUDA. You can't do it in OpenCL, right? OpenCL would be completely out of the question.
It's only Bonsai, and the rest is also Bonsai.
It's also Bonsai. Yeah, it's all Bonsai. So the CUDA code is running on the GPUs, and the MPI code is running on the cores. Yeah.
Two questions. The first one is, we know that you cannot program, you cannot parallelize every kind of operation in GPUs.
Yeah.
There are certain types of operations.
Yeah.
So, to what extent you can include other physics in this simulation beyond just gravity? I mean, calculating, I don't know, stellar evolution or fluid dynamics could be included and yet get all this performance in this cluster or not?
No way.
Okay.
Right. This is so optimized for gravity, but I mean you lose performance definitely. But if you would put in stellar evolution, which is not so very hard actually, you would use the CPUs on the machines to do the stellar evolution. And that means that your communication bottleneck will start playing a role again. So we would like to see a new supercomputer, they're building at the moment actually, with fewer nodes, powerful GPUs, and 32 cores per GPU. So more powerful nodes in total. And that's exactly what they're building.
But it means that a richer physics will become a bottleneck.
Yeah. Well, that is load balancing, right? That you have to fine tune and fine tune and fine tune. You have grad students to do that, right? I mean, that's not the professor's work. but adding stellar evolution is doable. Adding hydrodynamics is a complete nightmare because hydro works on a different time scale than the gravity and the stellar evolution. So hydro will be hard, but we will first try to do this with stellar evolution.
Okay, my second question is, okay, we are obsessed with the idea that we need all this amount of decimal digits to simulate the universe. But my question is if the universe itself actually uses infinite decimal places. You know, if you think about a 3-star system, a real 3-star system, maybe if you change, I mean physically, the composition of one of these stars and change a little bit the interior structure of the star, you will get a completely different evolution. So my conjecture is that actually nature doesn't use infinite decimal places to calculate the evolution of the systems.
I don't know what nature does, right? I know what it looks like. And we mimic that, right? But the fun thing, so what you hint at, the fun thing in this analysis using Brutus, right, showed to us that we can get away with energy errors as large as 10% of the system's energy and still get statistically indistinguishable results. So for my knowledge, nature may as well be calculating with 10% energy conservation rather than with 100% energy conservation. And you would not be able to see the difference.
I feel that nature doesn't make.
No, nature may not do any calculation. Yeah. I don't know.
I have a very point question is data management. How do you deal with the data, the snapshots you get out of this?
Yeah, we write snapshots for the galaxy, and one snapshot is 26 terabytes. The whole archive is not produced yet, but will be 4 petabytes. What do you do with it, right? You can't ship it over the planet. The only way to ship it is to load it on hard drives and put it into a container in a ship, literally.
Oh my goodness.
You can't do it over the internet.
How do you compare your calculations with the actual astronomical data? Because in nature, there is dark matter, and you don't include that matter, of course, in your calculations there.
Well, we put in dark matter via particles. We put in dark matter, but no, not in a way we think that, well, you know, in a sort of approximate way as, you know, as a numerical trick, so to say. But the comparison will be, in the end, with Gaia. So you have the positions and velocities of stars measured by Gaia, and you have the positions and velocities measured in the simulation, and that we're going to compare. That's how we're going to do the astrophysics.
So you will wait for data from Gaia?
I don't have to wait. There is already data from Gaia.
Okay.
Gaia is fantastic, right? The already data is already coming in. Yeah.
Is there any way of reducing the calculations by not considering the interaction between two very far stars? Because you are calculating n times n stars.
Yeah.
But if there are some stars very far apart, then you cannot, well, you can say they don't interact. Right?
But they do interact, right? They do interact.
But they're so far apart that...
But they still interact.
But this is precisely the idea of the trickle.
Yes.
Yes, try to
remove the n squared. So limit the long-range force operations, the number of long-range force operations.
So it's more particles are not removed, but they are summed up to a bigger particle.
Yeah.
Right?
Okay, no more questions?